Welcome back to another video. Here, we'll talk about mean and variance in joint probability distributions. As you may remember, a marginal distribution represents the probabilities of one variable, irrespective of the other variables, in a multivariate distribution. For example, in a joint distribution with variables like height and weight, the marginal distribution of height only looks at the probabilities or frequencies of height, ignoring weight. Marginal distributions help us focus on one variable of interest, even when it comes from a broader context with multiple variables. When we calculate the population mean of a marginal distribution, we are essentially finding the average of the variable of interest, like height, across the entire population just for that one variable. In a multivariate setting, the mean of a marginal distribution can sometimes require summing out or integrating over the values of the other variables. This process isolates the marginal distribution from the joint distribution. Once we have the marginal probabilities, the concept is the same as before. The mean is a probability-weighted average of the variable's values. The variance of a marginal distribution describes how spread out the values of the variable are around its own mean. Similar to the mean, when calculating variance for a marginal distribution in a multivariate setting, we first isolate the marginal distribution. Once isolated, we find the weighted average of the squared differences between each value and the marginal mean. This measures the variability in the data for that one variable, independent of others. Suppose you have a joint distribution of random variable x and y, and you apply a function such as x plus y to transform it into another random variable z. The expectation, or mean, of z tells you the average value of z over all possible outcomes of x and y, weighted by the probabilities of those outcomes. If we want to find the expectation of z, we need to find a double summation in case of discrete joint distribution, or double integration in case of a continuous joint distribution, of x plus y multiplied by the joint distribution as shown here. As x can be factored out in the summation over the domain of y, and y can be factored out in the summation over the domain x, both inner summations are simplified to the marginal distributions of x and y, respectively. This shows that expectation of z, irrelevance to whether x and y are independent or not, always simplifies to expectation of x plus expectation of y. We know that the expectation of x plus y, irrelevance to whether x and y are independent, always simplifies to the expectation of x plus the expectation of y. If we have weighted random variables, such as alpha x, then the expectation of alpha times x is the same as alpha times expectation of x. The two principles above combined can handle sums of weighted random variables. The expectation of alpha x plus beta y, where alpha and beta are constants, is given by alpha times expectation of x plus beta times expectation of y. This means you can scale or weight random variables, and the expectation respects those weights. This can be extended to handle sums of many weighted random variables. This property holds because the expectation is linear. Intuitively, the expectation is the average value of a random variable over its probability distribution, and adding or scaling random variables corresponds to summing or scaling their averages. If there are random variables such as x1, x2, up to xn, the expectation of their scaled sum is the sum of their scaled expectations. This holds regardless of whether the variables are independent or dependent, because the expectation is a linear operator. In a more general setting, the expectation of scaled summation of two functions of x and y is the same as the sum of their scaled expectations. Finally, only for independent random variables, we can have that the expectation product of two independent random variables is the same as the products of their expectations. We will discuss this further in the covariance and correlation video. Population variance measures the average squared deviation of a random variable from its population mean. It tells us how spread out the values of a random variable are around its expected value. When we scale x by a constant alpha, the new random variable stretches or compresses the values of x, which affects how far the values deviate from the mean. Variance of alpha times x is the expectation of square of alpha x minus expectation of alpha x. Expectation of alpha x can be simplified to alpha times expectation of x. we can factor out alpha and bring it out of expectation with a power of 2. Linearity of variance simplifies the variance of alpha x plus beta y for independent x and y random variables to alpha squared variance of x plus beta squared variance of y. If x and y are not independent, the variance of scaled sum of x and y would need to count for their dependence through measuring their covariance. For dependent variables x and y, the variance of alpha x plus beta y is alpha squared variance of x plus beta squared variance of y plus 2 times alpha times beta times the covariance of x and y, and the variance of alpha x minus beta y is alpha squared variance of x plus beta squared variance of y minus 2 times alpha times beta times the covariance of x and y. We will discuss covariance further in the covariance and correlation video. Let's go over an example together. We are given the joint distribution of x and y, and we are asked to find the expectation and variance of x and y. We will start by find the mean and variance of x. You can pause the video here and take a moment to answer this question. We start by finding the marginal distribution of x. To do so, we sum up over the corresponding column for each value of x. For example, the marginal probability of x being equal to 1 is 0.01 plus 0.02 plus 0.02 plus 0.15, which is 0.20. Similarly, we can find the marginal probability of x being 2 and 3 to be 0.25 and 0.55, respectively. Then, we need to find the product of each value of x with its corresponding marginal probability to populate the x time probability of x. Once we have these products, their summation gives us the mean or expectation of x. So, mu of x is 2.35. Finally, to find the variance of x using the computational formula, we need to find the expectation of x squared. Expectation of x squared is the sum of x squared multiplied by its corresponding marginal probability. That is 1 multiplied by 0.2 plus 4 multiplied by 0.25 plus 9 multiplied by 0.55. As the last step, we need to subtract the square of mu of x from this summation to find the variance of x. So the variance is 0.2 plus 1 plus 4.95 minus square of 2.35, which is 0.63. What about expectation and variance of y? Please pause the video and try to find these values by yourself first before checking the solution. We start by finding the marginal distribution of y. To do that, we sum up over the columns for each value of y. Then, we need to find the product of each value of y with its corresponding marginal probability to populate the y time probability of y. Once we have these products, their summation gives us the mean or expectation of y, mu of y. Finally, to find the variance of y using the computational formula, we need to find the expectation of y squared, which is the sum of squared of y multiplied by its corresponding marginal probability. Thank you for listening to this short lecture on mean and variance in joint probability distributions.